So we got a special chemistry topic right now, and this is something that is somewhat of a legend in the world of chemistry, at least in popular notions of chemistry, and that is HF, hydrogen fluoride, or hydrofluoric acid. So this is something that anytime you run into any sort of discussion about chemistry and this compound comes up, a lot of people will immediately say, whoa, 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 we don't want anything to do with that. This guy is the stuff of legends. And I'm basically going to take this opportunity to kind of take some of the urban legends away from HF, because while some of them are relevant, a lot of them are just that. They're just overhyped legends. So hydrofluoric acid, while it is certainly something to be respected, without a doubt, needs to be respected like any corrosive or toxic substance, it definitely isn't a chemical that is really scary in the ways that certain other chemicals might be. So HF is on a scale of 1 to 10, maybe a 6 in the world of hazardous chemicals, at least in my opinion. I will basically say that I work in a facility that uses large quantities of hydrofluoric acid, aqueous hydrofluoric acid, which means that it's HF and water, a water solution of hydrogen fluoride, which is popularly known as hydrofluoric acid. And we use it for etching and, of electronic semiconductor components. So, get to see how HF is used in industry. And when you're exposed to something at that scale, you kind of get to see how it isn't this crazy wild thing that it often is put out to be. So, start off with my high school chemistry days. Now, I was going to make a video display presentation thingy with visual aids in it, but I'm too lazy and don't feel like it. So you can just listen to this. There's not going to be a whole lot of visual information. In reality, this TV screen is probably too small to properly convey it on the video anyways. So we're going to talk about HF and all of its glory. So, HF is a very, very, very simple compound. It is hydrogen, H, and fluorine, F, one of each atom, bonded together. And whenever I took high school chemistry, we started doing reactions in the labs, and acids obviously are a very important thing that you get to use in any chemistry lab. And I will definitely recall that hydrochloric, HCl, hydrogen chloride, so this guy, HCl, often called muriatic acid, was the go-to acid in high school chem labs. And then we had sulfuric acid. Okay, sulfuric acid, H2SO4, yeah, that's a common, very well-known acid. But then there was also hydrobromic acid, or HBr. And then going down the periodic table, we also played with hydroiodic acid, HI. And going down farther, there's also theoretically, hydrogen astatide. I don't know what the pronunciation would be for the acid, but astatine is a very rare radioactive element, and we basically knew that by looking at our periodic tables, and we can basically just pretend it doesn't exist. But we never ever mentioned or even talked about, or definitely didn't play with, the top dog of the halogen acids. So you got iodine, bromine, chlorine. What about fluorine? The first of the halogens. Why, if we got HCl, HBr, HI, where's HF at? And I never got to touch, mess with, or use HF in any chemistry course I took in high school, which was 2 of them, and in college we had several chemistry-related courses, either general chemistry or various labs related to my to the environmental field. Never touched hydrogen fluoride or hydrofluoric acid. And then I start, somehow along that time, eventually learned what HF was, and learned via the internet about its legendary properties. So what are the legendary properties of HF? Now HF obviously can exist in its anhydrous, water-free form, just a HF, and that is a pure substance, which is at standard temperature and pressure is a gas, but it compresses and liquefies very readily. It has a low vapor, a pretty low vapor pressure at room temperature. It can be stored in a gas cylinder. But then there's also HF, H2O, which is the stuff that comes in the plastic bottle that you would see in any chem lab type environment, and that's your acid, hydrofluoric acid. Commercial grade HF is typically sold as a 49% solution of hydrogen fluoride in water. And the stuff that we buy in the semiconductor industry tends to be that concentration. So, the stuff of legends. So what's up with HF? So HCl, you get some HCl, hydrochloric acid, on your skin, what happens? Well, you get a burn, right? The acid is very corrosive because it has a lot of hydrogen ions that will protonate compounds that are part of your body. And it will react with stuff that's in your skin. You'll get a chemical burn. It will damage the tissue. It's kind of the chemical equivalent of touching a hot stove and leaving your hand there. The tissue will be destroyed by the energy released from the hot surface or the chemical reactions that happen with the acid. And with HCl, the damage is pretty much confined to the area where the acid touched the surface and didn't get rinsed off, because obviously, if you rinse the acid off quick enough, the damage is going to be pretty limited. Especially with HCl, that's not a horrible acid to get on your skin if you're right by a sink and you can rinse it off. But HF has an extra little element to it, an element, pun intended, and that's the fluorine. So, chlorine, HCl, I'm just haphazardly writing these symbols up, or these formulas up here, but HCl, the chloride part of that, human body is filled with lots and lots of chloride. Chlorine is a very common element in the human body. We have lots of chloride in our bloodstream. Our bloodstream is about 0.9% sodium chloride. Salts, there's a good amount of chloride already in your body, and a little bit of extra chloride from some HCl is not going to hurt you or do much damage. It's more of the protonation, the protons digging into the other compounds that make up the skin, that is why HCl is a problem. But with fluorine is a little different. And fluoride, I should say, because in a solution of hydrofluoric acid, it's partially dissociated. So the fluoride ion and a hydrogen ion, or proton, are kind of in the water, kind of zinging all over the place. So you got this fluoride ion. And fluoride has a very, very high affinity for all the elements over to the left side of the periodic table. So, sodium, potassium, calcium, magnesium are attracted to fluoride like flies on shit. So, you get some HF on your skin, and you don't really realize it right away because the HF isn't quite as acidic as HCl is, because the fluoride and the hydrogen bond is such that that acid doesn't fully dissociate in water. And you have the HF on your skin. It could be a little drop like that, a little tiny bit of HF if you're being dumb enough to use HF without personal protective equipment. You get a little blob, a little spot of HF on your palm of your hand, and you go like this, and you kind of just wipe it, and you go about your day, and you wake up the next day, and here's the stuff of legends. There's like this white spot on the palm of your hand, and it hurts really bad, and it does not look good. So what's going on there? Well, fluoride has gone into that area, and it has gone into holy matrimony with all of the calcium, magnesium, sodiums, and potassiums in that area of your skin. And these elements are important electrolytes, and obviously they're important for the functioning of most of the organs of most of the cells in most living organisms. You got to have the right concentration of sodium and potassium, calcium and magnesium to maintain the cells and the fluids that kind of fill the cells. So fluoride comes along, and it finds its friend calcium, and they go down and they get married and live happily ever after. They are not coming apart. So what's this rock right here? Now, this is, according to my rock collection, this is a sample of fluorite. Fluorite. Or fluorospar is the old name for it. Okay, fluorospar, which is CaF2, calcium fluoride. This stuff is completely insoluble in water. I can throw this in a bucket of water, come back 1,000 years from now, and it will look exactly the same as it did today. And that's what happens here. So all those calcium ions that are floating around in your cells of your hand or your bloodstream or your whatever, find a fluoride, now they turn into this. And it's a white powder that's just kind of, well, I'm out of commission now. Fluoride and I are now a couple, and see you later. And the calcium stops doing its calcium ion job, and now your cells die. And that's why HF has the toxicity that it does, because it takes these elements and it forms compounds with them that are more stable than the compound it was in the cell or in the bloodstream or whatever. It's no longer, in some cases, it even turns into a insoluble particulate matter, precipitate, that is a solid instead of an aqueous solution. So whenever you hear about HF burns and how nasty they are, it's because of this. Because the fluoride grabs a hold of all the other elements and it doesn't let go of them. Now you'll hear the stories about how a splash of 49% hydrofluoric acid on an area, say the size of the palm of the hand, a few dozen square centimeters, could be fatal. Well, that's because you got enough fluoride into the body where it takes out enough calcium ions to give you hypocalcemia. All right, and I'm not spelling it right, but hypocalcemia, not enough calcium. Calcium ions are important for the nervous system, they're important for the heart, they're important for all sorts of systems. So take away enough calcium ions and you got a problem. Anybody who's exposed to HF, what the typical antidote is you identify where it landed on the skin, and you wash that off with water for a good 5, 10, 15 minutes or so. And then usually there's a cream that contains calcium. Calcium gluconate is one example. And you rub that cream on the area that has the HF exposure, and you wait, for a few 5, 10, 15 more minutes, depending upon what it says on the tube to wait for. And then you rinse that off and you observe the area. If you get any redness, you do it again. And that's really the basic treatment for a hydrofluoric acid exposure. Somebody who has a really large area exposure in their body, you'd send them to the hospital just so that they're there and they can get saline solution and all that stuff if they need it. But in general, the whole idea is you got to feed these fluoride ions enough calcium, magnesium, sodium, potassium so that you don't run out of the electrolytes, which is what all of these elements would be. And that's the basics of fluoride poisoning. So what concentration of HF do you need to cause this problem? It's pretty high. So we're talking like percent level concentrations here. So you got to be playing with like 1, 2, 3, 4, 5% HF until you start running into this issue. A lot of people buy into a conspiracy theory about fluoride water, fluoridated tap water. So sometime back in the 20th century, people realized that if you add fluoride to drinking water, that it reduces cavities in the teeth. Okay, how does that work? Let me be right back. I'll be 5 seconds here. Fluoride, right? So what's this stuff? Toothpaste. This is a Peroxicare fluoride anti-cavity toothpaste. It contains 0.24% sodium fluoride. 0.24%. That is 2,400 parts per million of sodium fluoride. I think that's actually the fluoride ion, 0.24%. So how does fluoride, in either in this or in water, prevent cavities in your teeth? Well, what are teeth made out of? Teeth are made from calcium phosphate, or apatite as it's often called, no pun intended. Apatite, not to be confused with appetite as in eating stuff, even though we're talking about teeth here. So the apatite is something like Ca3PO4, and some water molecules and some crazy shit that I'm not even going to begin to write up here. But apatite, calcium phosphate, when it's exposed to acids, say acetic acid, which is something that may be formed when bacteria metabolize sugar in your mouth, that is corroded by the acid. So that causes tooth decay. The acid etches down into the teeth and goes through the enamel and causes a cavity, causes a hole in the surface of the tooth. You got to go to the dentist and have that fixed. But what happens if we take that calcium that's in the apatite and we convert it to fluoroapatite? We put fluorine atoms in there. Suddenly, let's just be simple about it and just say that it's that compound. That is very resistant to corrosion by the acids that would be produced by food and bacteria. Even the phosphoric acid that's in Coca-Cola is not going to corrode calcium fluoride. So the fluoride ions that are in the tap water, or are in this, convert some of the surface molecules of your teeth into fluoridated material that can better resist acid, can better resist corrosion. It's the entire basis of water fluoridation. It's why they put fluoride in toothpaste. Now, the concentration that's in here is so low that it doesn't scavenge up enough calcium ions from the rest of your body to give you toxicity. Now, if I was to be a dumbass and suck down this entire tube of toothpaste, well, I would probably be puking it all up. But if I managed to not puke it all up, you might have like a little bit of fluoride toxicity. But if I went and ate a few Tums, a few antacid tablets, drank a few glasses of milk, I'd probably add enough calcium to counteract the fluoride. Not something anybody wants to do, but theoretically the chemistry works. And this is the whole basis for HF's legendary performance at being toxic, is its affinity for calcium, also magnesium, potassium, and sodium. Now this has sodium fluoride in it. So how does sodium fluoride, if it's not acid, how does it react? Well, it's the old school, high school chemistry double displacement reaction, right? So you got sodium fluoride, NaF, plus, just say Ca, what is it, 3 PO4 2, all right, I think that's it. And then you react those two together and you get CaF2. Of course, this is unbalanced equation, plus sodium phosphate, which is the stuff that I use to clean the walls before painting, right? Trisodium phosphate, right? That's the reaction that would happen when this touches your teeth. This stuff's soluble in water. You rinse your mouth out, you spit it into the sink. No big deal. And you get some calcium, you get some fluoridated enamel on your teeth that can better hold up to the beer or the Coca-Cola or whatever acid stuff we're eating, whatever bacteria are producing that is corrosive to our teeth. And it's a marvel of the modern world. So what happens if you swallow the toothpaste? Well, it goes into your digestive system and it starts scavenging up calcium ions, and also sodiums, potassiums, magnesiums. And assuming that you don't have too much fluoride, it just uses some of the calcium. It's not a big deal. Assuming that we get enough calcium, it doesn't matter. So when I hear these conspiracy theories about how water fluoridation, fluoride is added to water at like 0.7 parts per million, 0.7 ppm. This toothpaste contains 2,400, well over 2,000 times more fluoride per unit weight than the water does. But people worry about water fluoridation. Oh, it's forced medication and all these various conspiracies. You go back to the 1950s and you hear that. Okay, whatever. So, fluoride is the toxicity of it, and HF, hydrofluoric acid, which is the original discussion, it's, the toxicity of that's very, 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 very dose dependent. We don't start seeing problems until we have high concentrations. So, what else about HF is legendary? So wasn't there that show Breaking Bad? I didn't watch Breaking Bad, but a lot of people did. It was a very popular TV show. Walter White, was that his name? I think it was. Manufactures methamphetamine. Makes a lot of money doing that. Because people want methamphetamine, so that's it. And his knowledge of chemistry was applied to many other nefarious activities in addition as a result of being involved in a black market industry. And I do remember reading about an episode where somebody was murdered, of course, and the body had to be eliminated. All right, what do we do? Well, you could dig a hole, the old standard method, but no, Walter White decided to dissolve the body in hydrofluoric acid. Oh, great TV stuff, right? So HF in a bathtub in this house, pours HF into the bathtub, probably straight up 49% liquid HF, aqueous acid, puts the body in there and thinks it's going to just decompose to nothing. Well, hydrofluoric acid being very corrosive to ceramic, glass, metals, etched through the bathtub and then went through the floor of the house. At least I think that's what I remember reading about the episode. I didn't watch it. Hopefully I'm telling the story properly. But dissolving bodies in HF. Is that, it certainly makes for dramatic television, but is it practical? And I can tell you right now that if I was confronted with a situation where a body, human or otherwise, had to be dissociated, I would not use hydrofluoric acid. Never. Okay, this is not the shit to use. My first choice would probably be sodium hydroxide, NaOH, caustic soda. That will basically turn everything except for the bone into a liquid mush that would go down a drain. All right? Sodium hydroxide, that's lye. It's what the guy put on his hand in Fight Club to when you're making the soap and burned his hand. Sodium hydroxide. You could also use, if you wanted to be classy and you wanted to be expensive, you could use KOH, which is potassium hydroxide. It will do the same thing, it just costs more money. Right? But these two substances would work very well for that. But the bones will not dissolve in these compounds, in these solutions. So if I had to then make sure that the bones were dissolved, I'd probably choose something like Piranha Solution. Piranha, that would be sulfuric acid and hydrogen peroxide. So it's basically a mix of these two chemicals, and these basically, this hydrogen peroxide becomes a very aggressive oxidizer, and it will burn off any kind of organic material. And the hydrogen, or the sulfuric acid, basically acts as a really good catalyst. It makes the peroxide very angry and makes it attack organic matter like a bunch of piranhas. That's why they call it Piranha Solution. We also use this in the semiconductor industry to strip off organic contamination from the devices. So this would work too, but this generates a lot of heat. It's very violent. It's very energetic. You have to keep adding peroxide as the peroxide is used up. That's why that would be a second choice. But it's definitely more aggressive than caustic soda. It's just not something that's easy to deal with. Whereas caustic soda is pretty easy to handle compared to this stuff. So Walter White and his body dissolution in hydrofluoric acid is nothing more than a television dramatic plot element. The HF, given enough time, and it would probably break down the body, but it would be just a nasty, disgusting mess that then is very, 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 very bad to deal with. It'd be far more problematic to deal with the residue that's left over than to deal with the body itself. In my opinion, from HF, HF just is not the material for the job. If you want to, say that that's a job for anything. So, what's HF used for? I mean, obviously I said electronics, etching. So, hydrofluoric acid was discovered in practically the Middle Ages, maybe the 16 or 1700s. And they manufactured hydrofluoric acid by taking a rock like fluorspar, so calcium fluoride, and adding to it concentrated sulfuric acid. Sulfuric acid is kind of like the king of the mineral acids here. You can basically add sulfuric acid to any salt. Sodium chloride, potassium chloride, calcium fluoride, sodium bromide, doesn't matter what it is, and you'll get the resultant acid. So this actually makes HF and gypsum, calcium sulfate, are the products of this reaction. So this is how hydrogen fluoride is still manufactured to this day in 2022. The same reactions are used today that were used, 400 years ago to make this stuff. Now obviously this product, this HF that comes off the end of here, is not high purity, so they run it through some distillation and filtration steps to purify it before selling it to the people that need it. And then once this HF is made, it gets used either directly as an etchant in the electronics industry, or they use this to make fluorine, the element fluorine, good old F2. And there's actually documentaries out there on YouTube about the discovery of fluorine. This is one of the most storied elements in all of chemistry because this is so reactive. Fluorine is an incredibly reactive element that it was very, very difficult to isolate. And several people died in the process of trying to isolate fluorine from hydrogen fluoride. So going from this to this is a big step forward. And you have to use electricity to break this apart to form fluorine. Use an electrolysis cell, and you split the hydrogen off of the fluorine, and you collect the fluorine. Then the fluorine can be used to manufacture things like Teflon, tetrafluoroethylene, polytetrafluoroethylene, all sorts of Gore-Tex. What else in our daily lives has fluorine in it? The old Scotch Guard, that was an old fluorinated chemical that they added to fabric to make it water repellent. Lots and lots of really, really crazy stuff that's been made using fluorine chemistry. And this basic reaction of manufacturing hydrogen fluoride and hydrofluoric acid is critical to that. So I'm talking about this stuff, toxicity here. You'll go out and you'll read articles and things about, especially about electronics. Oh, to manufacture your smartphone, they had to use a certain amount of hydrogen fluoride to etch the chips that are inside that phone. Like, oh my God, what's the impact on the environment here? Like, what is this doing to our planet? Oh man, how bad is it? Okay. So I've basically been circulating around this whole time the same set of chemical reactions. So HF, we use HF to etch our silicon wafers, our silicon dioxide films off of our silicon wafers when we manufacture computer chips. We use it to strip off certain areas. But the HF isn't completely used up in that process. So some of it, when it etches the silicon dioxide, SiO2, it makes Si. If you're doing it anhydrously, like in a plasma etch process, a dry etch process, you make silicon tetrafluoride. But if you're doing it in water solution, you make fluorosilicic acid, which is, I think it's H2SiO4. And what do we do with that? And what do we do with the HF that's left over that we don't use in the reaction? Well, we send it back to the earth from which it came, right? So, in any electronics facility, or probably any facility in the world that uses hydrofluoric acid, they have to treat the acid to dispose of it. So if they aren't going to fully consume it, whatever's left over has to be treated. It's easy. HF plus we add calcium hydroxide, CaOH2. And what is this? Calcium hydroxide, what's that? That's lime. Hydrated lime. So when you go to the hardware store and you need some lime for your garden, that's what it is. Calcium hydroxide. And that forms CaF2 plus H2O. And suddenly, we're back to this. The mineral that's here is the same thing that's produced by this reaction. It's all that nasty hydrofluoric acid is back to the rock from which it started. Because remember, we take this, we throw some sulfuric acid on it, and it makes HF. We use our HF, and when we're done with it, we don't want it anymore. We throw some calcium hydroxide, some lime, which is an abundant, product that's produced from limestone, calcium carbonate, and it goes right back to where it started. So it's out of all the things that are waste products in the world of human beings and industry, hydrofluoric acid is actually one of the very easy ones to deal with. This is an extremely simple process. When you use your bathroom and you flush the toilet and the stuff goes down the drain and goes to the sewer treatment plant of your community, wherever you're at, the processes that they have to use to treat that waste material are far more complex than this. So this is simple stuff. This is easy stuff in the world of waste treatment. So we can use hydrofluoric acid and not negatively impact the environment. The biggest thing you're doing is just using a lot of energy, You know, you got to manufacture the sulfuric acid, and you got gypsum left over. Well, what can you use gypsum for? So the byproduct of making HF from sulfuric acid is gypsum. What's gypsum? Gypsum. Plaster. Drywall. Gypsum. It's everywhere. Why not take that gypsum and use it to make stuff that we need gypsum for? And that happens all the time. Whether it comes from making HF or whether it comes from burning coal, we collect the gypsum and we use it to build buildings. So there's a lot of things that happen that are hidden from view that really make these processes not as nasty as they might seem. Obviously, though, anytime anybody's using this product, they need to carefully handle it. But if this is released to the environment, the effects are going to be very localized. So if I spilled a 55-gallon drum of hydrofluoric acid, 49% in my yard out here, I would cause a pretty bad impact over an area maybe 20 feet in diameter. It would chew up all the calcium in the soil. We'd make some calcium fluoride. We'd kill every organism there is there with the corrosivity of it. And the pH would be off, and the soil chemistry would be different. But it wouldn't really spread outside of that zone, that area, because this is so reactive. It's sort of the opposite problem that we have with carbon dioxide. So we're dumping, 36 billion tons of carbon dioxide into the atmosphere every year. 36 billion. Okay. 36 and 3 commas. Tons, metric tons of CO2. Now, CO2 is this invisible inert gas. It doesn't really hurt anybody, right? I'm breathing out CO2 right now. What's the big deal? Well, it doesn't react with anything. It just exists. Okay? Obviously, you've got plant material and plant and algae and photosynthesis that's removing some of that. But in general, this is accumulating in the atmosphere as an inert material that absorbs infrared radiation and keeps the environment warmer as a result. So this is when you release carbon dioxide, the impact isn't local, it's global, hence the term global warming. So it's, that's how things can be sort of very localized and very, dramatic in the small scale, and then global, but not so apparent, at least not immediately. So that's HF, hydrofluoric acid. And obviously, if you were to ever be working with HF, proper personal protective equipment, it's probably like nitrile gloves. The higher the concentration, the thicker the glove you need. Anything that's like if you're dealing with the 49% straight solution right out of the bottle, it should be a heavy glove that has a lot of chemical resistance. You don't want to be using the real thin gloves. Face shield to keep any splashing away. A smock or an apron to keep any kind of splashes off the body. And then, of course, HF is somewhat volatile. So at 49%, there's a lot of vapor that's given off by that solution. So you want to make sure you're working in a fume hood or you're working in an exhausted environment where the fumes can be removed, or otherwise you'll smell. HF, it smells very acidic. It's a very stingy kind of smell. But it's not something you want to be smelling for long periods of time. So it's important to have good ventilation with it. But other than that, it's definitely not doesn't have the crown jewels of worst, toxic, nastiest chemical. Go find the Chemical Weapons Convention and read about some of the substances that are in that, and you'll run into some of the nastiest, worst chemicals that human beings have ever created. Okay, things like VX. All right. sulfur mustard, mustard gas, GB, all these various somewhat simple compounds that have crazy, horrifyingly bad effects on the human body. HF is nothing compared to that stuff. So HF is kind of the building block of the modern world. Every electronic device that uses a chip or a semiconductor relies upon hydrofluoric acid for its manufacture. And we can very easily manufacture and manage hydrofluoric acid in a safe way. Whereas these things here have no use other than causing death and destruction. So that's it. That's about as far as I'm going to go. It's long enough. And learn more about HF, hopefully. So, be good.